I'll almost learn how to set it up by the end of the semester. Okay, so in the next, I guess in the second part of the course, if you will, we will look at like the, I guess, slightly more advanced linear algebra thing, but also more cool and more important for applications. So today it will start with determinant. Do you guys know already something about determinant? I already mentioned it a couple times, right? And you might have heard it before. So, but it's good. It's like a very useful thing. So we will discuss this lecture and maybe part of the next lecture. It's also because determinant is like the precursor to eigenvalues and related concept of eigenvectors. And that eigenvalues and eigenvectors are essentially a precursor to singular value decomposition, which I like keep reiterating. That's like the holy grail of linear algebra. So we will eventually get there. That's like the cool thing about algebra or linear algebra, or even about mathematics in general, to like build up cool concepts from like lots of simple small things, and then you put them together, you have like an aha moment, and like you understand that stuff. So let's start today understanding determinant a little bit. So I will first try to explain it informally, just like on the paper. So what is a determinant? So determinant is a function from a matrix that assigns it a number. So in a sense, so first of all, it only works for square matrices. So remember that determinant is only defined for square matrices, n by n. Wouldn't have to be real, could be complex matrix and so on, but we will only be looking at real matrices, but they always have to be square matrices. And the determinant essentially is answer to the question, if you could only characterize a matrix with a single number, what would be the most descriptive number of that matrix? The number that tells us as much information as possible about the matrix. And that's exactly the determinant. So it converts an arbitrary square matrix to a number, which tells us a lot about the matrix. So let's look at some simple examples. So if n is 1, most like textbooks start with n equal 2, but like it actually starts at n is 1, right? I guess you could start with n is 0, which would be like completely empty matrix, but I guess that's a little moot. But already n is 1, you have a 1 by 1 matrix, right? No problem, MATLAB takes it, right? So what do you think would be a determinant of a 1 by 1 matrix? So this is 1 by 1 matrix, right? So it has some element A. So the determinant of this funny matrix A is, guess what? A, yes. The matrix is already one number, right? So I don't really have to do anything fancy to convert it to one number. And obviously the A contains as much information about the matrix as I could ever wish for. So it starts really only being interesting for 2 by 2 matrices. And remember, they always have to be square. Right? Even if you came late, still remember that determinant only works for square matrices. So if I have a 2 by 2 matrix, there the determinant starts being a little bit more interesting, because there I have a matrix A, B, actually quite a bit more interesting. I have a matrix A, B, C, D, right? General 2 by 2 matrix. And the determinant is AD minus BC. That's how it's defined for 2 by 2 matrices. That's what it is. So notice it is a single number, it is a scalar, right? Which I compute from the numbers in the matrix. We will do like a little bit like IQ or interviewing test. So for a 3 by 3 matrix, I have, let me write it here, because that starts becoming a little bit more funny. So I have a matrix with numbers A, B, C, D, E, F, G, H, I. Please don't confuse this I with a complex. There's nothing to do with complex numbers. That's just like standard ladder. So determinant of a 3 by 3 matrix, I'll write it down for you, is A times E times I plus B, F, G plus CDH minus GEC minus AHF minus DBI. Now don't worry, you don't have to memorize this formula. We will make sense out of it in a little bit. I just wanted to give you now a few examples of determinants of a small matrices. So this was for a 1 by 1 matrix, it's just the number, for 2 by 2, and this is for 3 by 3. So you can start noticing a pattern here. So first of all, this is only one term here, right? So this is one term. Here I have two terms, right? AD and BC, right? Here I have 6 terms. 6 terms. Also, like in the 2 by 2, you see that the terms are essentially like multiples of two numbers from there, right? A times D and B times C. And here in the 3 by 3 case, I have A times E times I and so on. So the terms are always like multiplications of 3 elements from the matrix. You can notice that, right? It was case in the 1 by 1 too, right? That's why like considering the 1 by 1 case too. There's just one, so there's just one multiplication going on, right? So what do you think, how do you think this would generalize? So if I write it like this, 1, 2, 6, what do you think would be the next one for a 4 by 4 matrix? I'm not going to write it down because it starts becoming complicated and we will study it from a different viewpoint. But like, you can consider this like an intriguing question. Yeah?
It's like the diagonals, if you keep moving column over, multiplied.
Or like what is like diagonals?
The generalized equation. Or sorry, is that what you were asking?
Yeah, no, I was asking how this sequence of number would progress. I don't want you to guess the entire formula. That would be even harder question. Right now, I just want you to guess how many terms it will have for 4 by 4 matrix. So we know that for 1 by 1 is 1 term, for 2 by 2 is 2 terms, for 3 by 3 is 6 terms, right? So I wonder how this sequence of numbers would probably continue. Just as a brain teaser. Yeah? That's right. The next one. Does everybody see a pattern there? The next one would be 120. So this would be for a 4 by 4 matrix. This would be for a 5 by 5 matrix. So this is n factorial. N factorial terms. Yeah, this is like prototypical, I guess, interviewing question that somebody gives you like a sequence of numbers and then guess what's the next one, right? It's sort of a funny question if you think about it. Like you have to like come up with some sort of rule that's hidden and as simple as possible, right? Because in theory this question doesn't really make sense, right? You can always like find a polynomial that fits these numbers or something like that. But if there is like a pattern, if there is some sort of like some logic behind it, as is the case in determinant, then this has some information in it. So there is n factorial terms, and I will get to the general formula, but that's not what I want to start with, because pedagogically or didactically it's better to first explain the determinant by explaining its properties, because the general formula becomes very messy. It's like very long and not very nice at all. Like for example, if I had a 10 by 10 matrix, then the 10 factorial is something like roughly 3.6 million terms, right? So this formula is not how you want to be computing your determinants anyway, right? So I will get back to the formula for general n later, but it's probably even more important to think about the properties of the determinant as a function and sort of like analyze what is going on. So one interesting thing we can look at, or we can discuss immediately, is that the determinant, and now I mean of a general matrix, is 0 if and only if the matrix is singular. So this is, I guess, one application of a determinant. And I think I will explain it a little bit after we learn some more about determinant. But this is like one application. This is what is the significance of that number. It tells us something about the matrix. So if you have the determinant for a matrix, it immediately tells you if the matrix is singular or if it's invertible. Right? If it's 0, then it's singular. If it's non-zero, it cannot be singular, it must be invertible. which is nice, right? Now for For 2x2 matrices, I can even easily write an explicit formula for the inverse of the matrix. The formula looks like this: 1 over AD minus BC, and here is what is called a cofactor matrix, like this. So this is an explicit formula for inverse of a 2x2 matrix. And you can notice that what I have here is 1 over determinant, right? This term is exactly 1 over determinant of A, which is compatible with this claim, because if the matrix is singular, then the inverse doesn't exist. And that's because this term would be 1 divided by 0, right? Because this is the, for 2x2 matrix, the determinant is AD minus BC. And if it's singular, the determinant is going to be 0. I cannot divide by 0, so I don't have, this formula is undefined for that case. So it all makes sense. So how about determinant of identity in the 2x2 case? So determinant of 1, 0, 0, 1. How much is it? 1. That's right. It's obvious from this formula line, right? And how about this matrix? Oh, I should make like a notational remark. So this is one way to denote determinant, just to say that and just put in the regular brackets the matrix. Another way to denote determinant, equivalent way, is to just do this. Is to just do like straight lines. So I could write it like this: 1, 0, 0, 1 is 1. So that means determinant of this matrix. The determinant is so important that it has like its own dedicated notation. So don't get confused. I will not be using this much. I don't like it very much, but you can like find it in the books, in the Strang's book. It's used quite a bit, these vertical lines. So that means determinant of that matrix. So let's practice the notation a little bit here. So I was asking, what is the determinant of this matrix? So notice that this matrix is almost the identity, except that I flipped the rows. Right? The first row became the second row, and the second row became the first row. Or equivalently, I flip the columns. Doesn't matter, right? So what is the determinant of this matrix? -1. That's correct. So notice one property here. If I flipped rows or columns in the 2x2 case, but we will see it also works in the n by n case, the sign of the determinant flipped. If I switch the rows or columns, that doesn't matter, the sign flips. I mean, I can show that in general, right? If I want to compute, let's practice this notation a little bit more, the determinant of this matrix. So I took my general 2x2 matrix A, B, C, D, and I flip the rows. So I do first CD and then AB. So my determinant is going to be CB minus AD, which turns out to be exactly minus of the determinant of AB, CD, right? So for 2x2 matrices, this works in general. If I flip the rows, equivalently I could also flip the columns, and I would find the same thing. The only thing that changes is the sign of the determinant. Okay. Yeah, the other question we could be asking ourselves, if determinant is like a mapping from a matrix to a number, right? And we discussed quite a bit linear mappings. So could it be that determinant would be a linear mapping? That determinant of A plus B would be determinant of A plus determinant of B. I haven't really defined yet determinant B on 3, but let's just think about these cases. Can this be possibly true? What do you think? So this means that the determinant would be linear in terms of being a linear mapping from matrices to numbers. So it doesn't matter if I first sum the matrices and then take the determinant, or first compute the determinants and then sum them as numbers. What do you think? Do you think this is true or not? Slightly tricky question. Well, let's take a look, right? If you don't know, let's take a look, because I think it's perfectly fine not to know. So let's try just identity, right? It's the simplest possible case. So if I just add two identities together, so that means it's the determinant of this matrix, right? Which is how much? 4. If I take determinant of identity, I know that's 1, right? So clearly this is not true, because if I do that I plus that I is just 2, and that's certainly not equal to 4, right? So this is absolutely not true, already for the 2 by 2 case. So there is no banana, no free lunch or whatever you like to eat. This is not so easy. It is not a linear mapping determinant. Nevertheless, there are some nice properties. And actually, the easiest way to introduce determinant for general n beyond 1, 2, and 3, for 4, 5, 6, or 1,000 really, is to define determinant by spelling out its properties. So rather than writing out the formula, which is like really ugly, and I will show you the formula, it's easier to just define it by saying that it's a mapping with specific properties. And this is what we start the slides with. But let me first give you some motivation why actually it's such an important thing to study the determinant. So you don't think it's just like some sort of weird mathematical concept, which might be cool, but determinant has tons of applications. So as you have already seen here, I can use the determinant appears in the explicit formula for inverse matrix. This is actually true for general n. This was the case for 2 by 2. In 2 by 2 matrices, everything becomes easier, so that's why I illustrated here, but it works for general matrices too. I can even use the determinant to write down an explicit formula for solutions of a linear system, assuming that A is invertible, so A inverse B. There is a very cool geometric interpretation of determinant. Have you ever heard that? What is determinant of, or let me make it a little bit easier, the absolute value of a determinant as a, yeah?
Is it the area that's swept out by the matrix?
Correct. In 2 by 2 case, it would be area.
Or volume or
In 3D, it would be volume, right? In 4D, it would be like hypervolume or something like that. And it works in ND too. So we will get there. We will get there. But I'm just like giving you a preview that determinant or the absolute value of even the determinant, the sign actually has also very cool geometric interpretation. You can think about what it could be. It will appear in a little bit. And probably the coolest linear algebraic application is eigenvalues. It turns out that eigenvalues of a matrix will be the values lambda such that A minus lambda I, this equation, the determinant is 0. So this is how we will get to eigenvalues eventually. But first we need to understand what is determinant, because eigenvalues are really defined through a determinant. All right, so let's look at the general case. Unless you have some questions to my notes here, like the determinant preview, if you will. I think it's like really good to like look at the 2 by 2 and the simple cases, because something you can already prove with the 2 by. This is like a perfect proof that this cannot be true, right? You just need one counterexample, so just pick the simple one. You don't have to do any fancy mathematics there. All right, so let's look at the general case. You are silent and therefore happy. So as I said, the determinant is a function that takes a square matrix n by n and returns a real scalar value. You could generalize it to complex numbers and so on. We will not do that yet. We will need to do that for eigenvalues maybe, but let's just think now about the real case. This is the notation, so that either that A or the vertical bars. And this is the most important thing. This is how determinant is defined for general n, for arbitrarily sized matrices. So it is a mapping from the matrix to the number, which has the following properties. So the first one is that the determinant of the identity is 1. Second one is, that's what we saw for the 2 by 2 matrix. So if you exchange 2 rows or 2 columns, then the sign of the determinant flips. You change the determinant from plus to minus or from minus to plus. The absolute value doesn't change, only the sign. Yeah.
So if you do it twice, if you flip two sets of two rows.
Yep, very good question. So let me repeat it for record. If you do this twice, then it means that you flip the sign twice, so then you are obviously back to the same number, right? Like here you can see it, like for example, if you flip the first and second row, then you do it again, then you are back to the same matrix. Then of course you have to, but it also works like if you flip the first and second and third, then you again get to the same number, which is sort of cool. But right now that's like a definition. Right, so it's not something we like debate about. This is how we define it. So yeah, you are right that from the definition it implies that if I do the flips twice, then I'm back to the same sign. And if I do them 3 times, then I'm back to the negative sign, right, or the opposite sign really. I mean, if I started with negative sign, then the flip gives me a positive sign, right? It's like multiplying by -1. That's what it really means. Clear? And the third property, that the determinant is linear. So be very careful about this linear, because I just showed here that it's actually not linear. So that means, how do we interpret the linearity, right? So what it means here, that means linear with respect to every row or column of the matrix. So this linearity means that if I take a matrix that looks like this. So let me explain this a little bit better. So the VT is just like a row vector. WT is also a row vector. And this says that if I have like a matrix, maybe I can write it like nicely. Actually, let me write it for the 2 by 2 case. That might be easiest. So if I do a matrix like this, so my original A, B, C, D matrix, where the first row I multiply by T. Then the determinant of this is T, A, B, C, D by this property. So this means if I multiply by a scalar the first row or second row or any row really, then I just get the scalar times the determinant. So that's one part of the linearity, and the other part of the linearity means if I add something to the first row, if I do this, then I just add the individual determinants like this: A prime, B prime, C, D. You see that? So if the first row is just like sum of some row vectors, A, B, and A prime, B prime, then the determinant just splits into 2 simpler determinants, if you will. And this rule here is nothing but the same idea for the general case. So this can be this is some matrix which has some rows, right? There is some row here, and so on. And one of the rows happens to be a sum of alpha times the row vector bt plus beta times the row vector wt. And this rule number 3 says that the determinant of this matrix is nothing but alpha times determinant of this matrix plus beta times determinant of this matrix. So when the other rows, they are held fixed. That's the critical thing there, right? That's why it didn't work here, right? In this version of linearity, which does not apply, I was changing the entire matrix. It doesn't work if you like change the entire matrix. It only works if you change only one row or column equivalently. So here it's all defined by rows. When we switch to rows, we could, because of columns, we can then prove it from these 3 defining properties. Actually, here is so this is how determinant is defined. It's essentially a function from a matrix to a scalar, which has these 3 properties. And then if we were like really strict about the mathematics, then we would show that such a function exists and it's unique. And that's true. You can believe me that. So these 3 properties are a good definition of a function. So any function that has these properties is called a determinant, and there is just one function like that. And from these properties, we will then derive some other properties which will help us to better understand what the determinant is, how does it work. So one thing we can notice immediately is this. So here I was multiplying by some scalar t just the first row, right? Or I could multiply the second row or row number 43, doesn't really matter. So it turns into multiplication by a scalar of the determinant. So if I multiply the entire matrix, and if it's an n by n matrix, what do you think I will get? Your first determinant exercise, you can like create like lots of very cool determinant exercises. It's like the prototypical thing you do in mathematics, right? You like say some axioms and you say the thing is defined like that, right? Like set theory, you lay out some axioms, and then you like think about what all these axioms imply. And like you discover cool things by doing that. So what do you think would be if I took a matrix A, which is n by n, multiplied by scalar t, what will the determinant of that be? Yeah, does someone else also have a opinion? Yeah, what do you think?
T squared times the determinant of the matrix.
Yeah, if n is 2, that's true. What about for general n?
T to the n.
That's right. Yes, exactly. T to the n and determinant of A. Correct. Because I just apply this rule n times, right? Because this TA means multiply every row by t, right? And this tells me that every row pulls out the t outside. So if I do that for every row, like if I did that here, I could write this, right? And here I could do t squared, A, B, C, D. And if it's an n by n matrix, then I of course get t to n. By the way, this also is compatible with what we said here, right? Because this determinant I plus I is just determinant of two identities, right? Which has to be 2 squared times 1, which is 4. So that's correct. That's a simple case. Okay, so those are the three defining rules of a determinant. And from these three defining properties, we can deduce some properties that then follow by logic. So one cool property is that if we have a matrix, and the matrix has 2 rows which are the same, or columns, but we will see later that doesn't matter if you look at columns or rows. So you can state all these claims either in terms of rows or columns. So let's just talk about rows for now. So if the matrix A has 2 rows which are exactly the same, then the determinant of the matrix is 0. So why is that? Now we have to prove it. Now this is not a defining property anymore. Now it's like a derived property, so we have to prove it. So that follows from the second property. The second property was if we exchange 2 rows or columns, then we need to flip the sign, right? But if we have 2 rows which are exactly the same, then if we exchange them, then the sign also flips, right? But if they are the same, then the exchange didn't really do anything, right? So it means that the determinant of A must be minus determinant of A, because the exchange didn't do anything. They were the same, right? And the only number, this is just a scalar, the only number with the property that the number times equals minus 1 times the number is 0, right? So that means that the only way this can be true is that the determinant is 0. Did you follow that logic? That's like a proof, essentially. Very, very simple proof. Shall I repeat that, or is it clear? It's essentially written here, right? If you interchange 2 identical rows, we get the same matrix, but at the same time we need to negate the value of the determinant. The only way this could possibly be true is if the determinant is 0. So from this we can conclude that if the matrix has 2 equal rows, like something like this, like some A and there is another A, so that these rows are exactly the same, then the determinant of this is 0. Okay? So from this, we can then subsequently derive that if we add a multiple of one row to another, then the determinant doesn't change. So I think here we are actually missing transposes. So sorry about that. Let me add them here. So those are supposed to be row vectors. And I started from a matrix that looked like this, that had like some rows here. There was some row AI transpose, and there was some row AJ transpose, and so on. So this is a matrix I started with. And then I decided to multiply the row AI by alpha and add it to row number J. And this is the matrix I get. And I'm curious, what is the determinant of this matrix? And it turns out that it's actually exactly the same as the determinant of the matrix I begin with. So this was my matrix A. Right, yeah, here it's not super clearly. So here, like one of these guys was AIT. It's also AIT, right? This is my A. A was absolutely general matrix. Oh, that could be anything. And what I did to A was that I took this row, this entire row, multiplied by alpha and added to this row. This is one of our elementary operations, right? I'm trying to like build up to something similar like the conversion to reduced row echelon form, which you should be no experts on. So I claim that the determinant of this matrix, where I did this operation, is exactly the same as the determinant of the matrix A I started with. And this is true because of the linearity, right, of the determinant. So here is what we had on the previous slide. So if we have a row like this, we can split it in two determinants, right? So this is exactly what I do here, because this is exactly the case, right? So the first matrix is where I just keep the AJT. That's just the original A matrix. And the second one is a matrix which has this part, right? The AIT is here and the AIT is here as well. So this is a matrix which has two rows identical, right? And what we have said here is that if the rows are identical, then the determinant is 0. This one is 0. Multiply by alpha, but whatever multiply by 0 is 0, right? So that means that the determinant of this matrix is equal to the determinant of the original matrix, which is interesting, right? Did you follow this? Yeah, the second part of the sum is this. That's a matrix which has this row duplicated. So the determinant is 0 based on what we said here. So the determinant of this like modified matrix, of the matrix where we apply the elementary row transformation, is the same as the determinant of the matrix A we started with. So this is nice. This will tell us how to actually compute the determinant in a more efficient way than using the crazy factorial formula. So there's another property of determinants, which is sort of simple. If you have a matrix with a row or column, if you want, which is all zeros, then the determinant is also 0. Now that's really trivial to prove, again from this property, from this rule number 3, right? Because if one of the rows is completely 0, then I can just write it as 0 times anything, right? And that will tell me that it's 0 times that thing, but again 0 times whatever is 0, right? In other words, the 0 row or column, the 0 can be factored out, and due to linearity, I have to get 0. So this immediately follows from the third property. So if I have a row or column full of zeros, then my determinant has to be 0 too. Okay? That was easy. Let's look at elementary matrices. So the idea here is what I'm trying to do is to find out how to compute determinant for a general matrix. Because now we have the defining properties, but so far we don't have a way, or we don't know an algorithm to compute determinant for a general matrix. And a good strategy is to first figure out the determinants of elementary matrices. Because we already know, and you now already know very well thanks to the midterm, that every matrix, and here we are doing just with square matrices, so it gets even easier than that, can be reduced to reduced row echelon form. And just by doing these three elementary operations, switching to rows, multiplying a row by a scalar, and adding a multiple of one row to another. That's exactly what this property was about, right? This was adding a multiple of one row to another, right? So here we actually already show that adding a multiple of one row to another doesn't change the determinant. That is cool, right? That's promising. So maybe we will be able to compute determinant of an arbitrary matrix efficiently. More efficiently than taking like n factorial terms. So the elementary operations, we know that they can be expressed in the matrix language as multiplication by the elementary row transformation matrices, right? Those are these E matrices. And based on the properties of determinant, we know that how they will change the determinant. So let's go a little bit more slowly. So if E is a matrix corresponding to one of these three elementary row operations, and the resulting matrix is the matrix A after applying this operation, so in matrix language it's just multiplying by E. So if it's a type 1 operation, it means swapping two rows. Immediately from the definition of determinant, we know that the determinant of B will flip the sign of determinant of A, or -1 times the determinant of A. Yep. If it's a type 2 operation, so it means multiply a row by a scalar value, again, directly from definition from the linearity with respect to rows, it just multiplies the determinant by alpha. Right? Funny case is if the scalar is exactly -1, because then you get the same thing, alpha is -1. And the third one was adding a multiple of one row to another. Well, from what I just showed previously right here, that does not change the determinant at all, right? That's what I discussed here. If you just add a multiple of one row to another, determinant doesn't change. So the determinant B, that's the modified matrix, that's this matrix, is equal determinant A, that's the original matrix. Is it too much information at once? Actually, let's look at some more concrete examples. So I will just like show it on 4x4 elementary matrices, because it's a little bit less messy than like putting there these dots on like arbitrary size matrices. The idea is exactly the same for general matrices, right? So the type 1 operation, meaning swapping rows, the matrix looks like this, right? This matrix swaps rows 1 and 2, right? You could easily figure out a matrix for swapping any two rows, really. I trust you on that. So what does it do to the determinant is, this is essentially just like swapping rows of an identity matrix, and determinant of an identity matrix, that was the first defining property of a determinant, was 1, right? So the determinant of this matrix was -1. Now we can come back to your question here. If I did another swap of rows, right? For example, multiply with matrix that swaps rows 2 and 3. Then I would get what? I would get 1 again. Yeah, and another swap would give me another -1 and so on. It doesn't matter that the swaps can like bring it back to the original state, right? Like if I swap then back, then clearly I have to go back to 1, right? Because I'm back at identity. Am I making sense? Yeah, and this is swapping rows 1 and 2. That's very obvious, right? Because this is actually a permutation matrix. Do you still remember permutation matrices? If I do this E1 times A, B, C, D vector, what do I get? I get B, A, C, D, right? So it's swapped the first two coordinates. And if I hit it with a matrix, then it of course swaps the entire first two rows. This is a permutation matrix. And its determinant is -1. In general, doesn't matter which two rows it swaps. It doesn't matter how big it is, right? So the type 2 one means multiply a row by a scalar. So it's diagonal matrix, almost identity, except that one of the elements is alpha. So in this example, it's multiplying row number 2 by alpha, right? You could easily write a matrix that multiplies arbitrary row with arbitrary number. What is the determinant of it? Well, from the second, or maybe the third one, the linearity, it's just alpha times determinant of identity, right? Which is alpha. So that's simple. And the third elementary matrix, that's the one. So here is an example that takes row number 1, scales it by alpha, and adds it to the third row. So if you have like a good mental picture of matrix multiplication, so there is another matrix living here and has some rows, then all the rows go through, and the third row, except for the third row, where the third row becomes the copy of the third row plus alpha times the first row. And from what we said before, this does not change the determinant of identity, so the determinant of this is just 1, right? Or I guess I could prove it directly. Yeah, we could prove it directly too, because this would be just alpha times determinant of a matrix that has 1, 0, 0, 0 here, so there would be 2 equal rows, which is 0. Do you see that? Or that's fairly simple. Or shall I write it down? Just to practice a little bit more determinant stuff. I think you're okay. Okay. All right. So more about elementary matrices. So this is a really important property which we will later generalize to arbitrary matrices. So what we see, from what we have just discussed, is if E is an elementary row transformation matrix and A is an arbitrary matrix, then the determinant of the product, EA, so meaning the row transformation applied to A, is just the determinant of E times the determinant of A. And this is because we know what the elementary matrices are doing, right? The first one is swapping rows, the second one is multiplying row by a scalar, and the third type is just adding a scale of one row to another row, right? In the first case, we know it changes the sign of the determinant, which means multiplying by -1, right? But the determinant of this is -1, so this is true. The same way for all the other matrices. So this, we know that this change of the matrix, this EA, changes the determinant by multiplying it by alpha, right? That's from linearity. But the determinant of this matrix is alpha, so I can just write it like this, right? Just alpha times determinant of A. And the same way for the third case. For the third case, this is actually 1. So that's actually simple. So for elementary matrices, I can it's actually, what is this called? It commutes with the product commutes with determinant. In the sense, it doesn't matter if I first multiply an elementary row transformation matrix with A and then take the determinant, or first take the determinants and then multiply them together. So for multiplication, this works, right? For addition, I showed you before, doesn't work. For multiplication, it does. Well, and then lots of cool things follow from this. This is not yet this is still just the beginning. So if you have an invertible matrix, we can reduce it to just identity, right? We are in the square case, it's n by n. So if I assume further that A is invertible, it has an inverse, then I can convert it to identity by taking the reduced row echelon, or the reduced row echelon form of invertible square A is just identity. And the way I get to the reduced row echelon is by a sequence of elementary row transformations E. So I apply a sequence of these elementary row transformations, I get to identity. So now using this property tells me something about the determinant of A, something very, very important. It tells me that the determinant of, so first of all, this is identity, right? So the determinant of this is the determinant of identity, which is 1. That's the first defining property of the determinant. Drink some more water. Look at this. Next, I know if I take an elementary row transformation matrix, multiply it with any matrix, I can write it like this, right? So I first apply it, I assume that this is my any matrix, and I can take the det E1 out of it, right? Then I can do the same thing for the rest. Then I can take the E2 out of it. And ultimately I can separate all the determinants, and I can take them all like this. So I find that this is just the product of the determinants of the individual matrices. Do you copy? And because those are elementary row transformation matrices, we know that they are invertible. So the determinants are non-zero, and I can take the inverse here. And so meaning I can divide by them. So I find that the determinant of A is exactly this. So this already tells me one way how I can compute the determinant of an arbitrary invertible matrix. I mean arbitrary but still square, and I assumed here invertibility. So this already tells us something interesting about how to compute the determinant in not completely general case. Another useful case, or a simple case where I can compute a determinant easily, is the case of a diagonal matrix. So diagonal matrix looks like this, and you can probably tell me immediately what is the determinant of a diagonal matrix, even without looking at this. There is the second or the third property, the linearity, which says that every row is linear, right? So I can write it as A11 times 1 or A22 times 1, right? So I can pull out all these coefficients and I will be left with identity matrix, and the determinant of identity matrix is 1, right? So for a diagonal matrix, determinant becomes really simple. It's just the product of all the diagonal elements. So do you follow the logic, like that all these things are derived from the 3 fundamental defining properties of the determinant I started with? Okay, and it gets a little bit more funny when I will want to consider an arbitrary matrix, but I think I will have to explain that on Wednesday. So do you have any questions to what I said about determinants so far? Maybe to take a look at it, let it sink in a little bit before we go to the other properties of determinants, because I think it's like a lot of information in a short amount of time. Any questions to that? Okay, so I think it's about time. Yeah?
Do you have a project this week?
Sorry?
Do you have a project this week?
I think so. I think I have something in stash. Why?
Is it posted on?
Oh, you mean I know? I meant I will post something on Friday, not for this week.
Oh, okay.
Yeah.
Sorry.
That's yeah. That's one of the benefits of being gunned. They couldn't really do anything. Okay, sorry. Yeah, there will be something on Friday. Yeah, right. Cool. All right. So more on Wednesday. Stay tuned.